Today we're going to be doing Inquiry 3.3, locating the epicenter of an earthquake. The first step that you need to take is to open your online textbook and read Finding the Epicenter, the Tortoise and the Hare on page 38 and 39. So if we go to our textbook, page 38 and 39 will be page 54 and 55 on the blue slider. So first step you need to do to find out more about the epicenter and about how fast P waves and S waves are is to read this reading passage right here. So once you have finished reading the reading passage, then you can open your CAMI document and continue with the activity. We're going to be using information from both the book and from this CAMI document to help us to find out where the epicenter of the earthquake is. And we'll find the epicenter in our final step. But to get to that point, let's first go to our textbook to the procedures that are on pages 40 to 44. So if I go there, page 40 is page 56 on the blue slider, and I'm going to just be following these procedures along. So I'm going to take you through the first part, and then we'll go back to our CAMI document in just a moment. Okay, we did step one. We read Finding the Epicenter, the Tortoise and the Hare. And then step 2 says for us to look again at our data from Inquiry 3.2 that we did yesterday and think, do you think that knowing that the earthquake was 4 minutes away from Bellingham is enough information to enable you to determine the exact location of an earthquake? Well, just knowing that an earthquake is 4 minutes from a location is not enough information to determine the location of an earthquake. Seismologists would also need to know how fast the earthquake waves traveled so they could compute how far away the epicenter was. And so the formula they would use is distance traveled equals speed at which the vibrations traveled times the time that the vibrations traveled. Also, knowing the distance from one station is not enough, since earthquake waves travel outward in all directions. This means that the earthquake could have occurred anywhere along a circle centered on a station. All right, so let's look at number 3. It says to use this graph, figure 3.7, and you will not be able to do this as carefully as we will in class because you would actually need to use a paper form of this and a note card. So we're just going to go over these things for those of you who are doing the lesson virtually. Okay, it says to look at the graph, and to learn how to use this graph, we have a couple of questions to look at. All right, question A says, if it took 4 minutes for the first P wave to arrive at the seismograph station, how far away is the earthquake's epicenter? Our hint says look on the P wave curve. So if we look at the P wave curve, which is the bottom curve, and we go about 4 minutes, the time traveled 4 minutes, and we come across and find where it intersects the P wave line, we will see that the distance was 2,000 kilometers. So this means the epicenter is 2,000 kilometers away from the seismograph station. All right, question B says, if the seismograph station were located 2,500 kilometers from the earthquake's epicenter, how long would it take for the P wave to arrive? So if we go to about where 2,500 kilometers would be and go up, we would see that it takes about 5 minutes. So 2,500, 5 minutes. It would take about 5 minutes for it to arrive. All right, question C. How long would it take the S wave to travel 2,500 kilometers and reach the seismograph station? So again, I would go up from 2,500, but this time I would see where it intersects the S wave, and that shows 9 minutes. So it would take around 9 minutes, maybe a little less, but almost 9 minutes. All right, and then letter D, using 2,500 kilometers, which wave traveled faster, the P wave or the S wave? Well, at 2,500 kilometers, we remember that it took 5 minutes for the P wave, but it took 9 minutes for the S wave to reach the station. So that means that the P wave is faster. Okay, and then question E. At 2,500 kilometers, how many minutes elapsed between the time the P wave and the S wave arrived at the station? Well, we just answered that. We said it was 4 minutes. So we could take S wave minus P wave equals the time, and so 9 minus 5 equals 4. Okay, if we think about the analogy in the story of the tortoise and the hare, the greater the difference between the two waves' arrival times, the farther the station is from the earthquake's epicenter. If the difference had only been 1 minute, for example, it would mean the epicenter was closer to the station. Okay, and then letter F. Considering the whole graph, how does minutes elapsed between the P wave and S wave arrival relate to the distance from the earthquake's epicenter? And so as we can see from our graph, the farther you are from the earthquake's epicenter, the more minutes there are between the arrival of the P wave and S wave. For example, right here at 0, there's not much difference in time between the P wave and S wave. But if we go way out here to 6,000, there is a greater distance between where the P wave and the S wave would be. So the farther you are from the earthquake's epicenter, the more minutes there are between the arrival of the P wave and S wave. Okay, if we continue on to step 5 on the next page, these instructions are going to show you how we would use the note card in class, and we would plot our 4-minute time here, and then we would take that out on our graph and find where that intersects. And we find that we are at about 2,500 kilometers when our 4-minute lag time matches up. Okay, now let's switch over to our text, or to our CAMI document for just a moment, and let's look at the information that's there. Okay, first you have 3 different seismograph stations. You have Station A, which is in Sitka, Alaska, Station B, which is in Charlotte, North Carolina, and Station C, which is in Honolulu, Hawaii. And on each of these seismograms, you can see the time that the earthquake wave started there. You can see the arrival of the P waves and then the arrival of the S waves. You can see that again on the Charlotte, North Carolina. It was 12:07 when they started recording this. And then here you can see the start of the P waves. Here you can see the start of the S waves. And you can see there's a little more distance between, there's a lapse in time between the P wave and S wave. And then, whoops, I'm sorry, I went too far. If we look at the one for Honolulu, Hawaii, we see the start of the P wave here, we see a little bit of a lapse in time, and we see the start of the S waves here. So we can see from this that it looks to me as if Sitka, Alaska is going to be closer to the earthquake, and it looks to me like maybe Honolulu, Hawaii is the farthest away. And that's just from first glance, just looking at the difference or the lag time in the P wave and S waves. All right, if we go on down and look at our earthquake data, we're going to use those 3 seismograms up at the top to help us find the time of arrival at the station for the P waves and the S waves, and then we're going to find out the distance there, and that distance will be based on our graph from our book. So Sitka, Alaska, if we look at our seismogram, the P waves first arrived at that station at 8:09. The secondary waves or S waves reached there at 8:13, and so there was a lag time of 4 minutes. So if we go back up here and look, we can see the P wave started at 8:09, the S wave started about 8:13. And so that's about 4 minutes difference. Okay, if we look at Charlotte, North Carolina, the P waves arrived at that station at about 12:10, and the S waves arrived there at about 12:15, and so that is a difference of about 5 minutes, and we can see that clearly here. right here about 12:10, right here about 12:15. So about 5 minutes difference in the time. And then Honolulu, Hawaii. 7:11 is when the primary waves arrived at the station. 7:17 is when the S waves arrived, so it was a lag time of 6 minutes. So in class, we would go back to our data table using the same method that we learned using our note card here. We would go back to our data table and we would find how far away. So the one that is 4 minutes away, we would see that it is about 2,500 kilometers away. And then the one that is from Charlotte, North Carolina, the distance from the epicenter is about 3,500 kilometers. And then Honolulu, Hawaii is 4,500 kilometers. And so we got that by interpreting our graph in the book. Okay, if we scroll on down, the students in the class are going to be using a special type of compass to help them draw the circles here. But I just wanted to show those of you that are doing the lesson virtually what your map would look like. Okay, here we have Sitka, Alaska, which was Station A. And using our compass, we would have drawn a circle that is 2,500 miles from the epicenter. And then for Charlotte, North Carolina, we would have drawn a circle that is 3,500 kilometers from the station, And then for Honolulu, Hawaii, we would have drawn one that was 4,500 kilometers. So we would have done that in class using our compass. Okay, and so the very last step for us is to locate where all three circles intersect or come the closest to intersecting, and that's going to be the epicenter of our earthquake. So if you look right here, where my cursor is, right here would be where the earthquake actually occurred. And that would be in California. Okay, those of you who are doing this at home, you can just use the data that we gathered here. If you have any questions about earthquakes or epicenters, then make sure that you send me any messages about any questions that you have. Before I go, let me just double check. Okay, just making sure I didn't leave anything off. I hope you have a great day.